So proof number 3 asks for us to prove an equivalent version of the Archimedes principle, the Archimedean principle. The Archimedean principle, remember, is the assertion that the set of natural numbers has no upper bound. In other words, however large you give me as a natural number, I can always find a natural number which is larger. The assertion that we're supposed to prove here is a little bit different. This assertion doesn't have to do directly with natural numbers in the beginning. Instead, it says if I pick up an epsilon greater than 0, and this epsilon is intended to be a real number. So for any positive real number, we can find a natural number such that its reciprocal is less than epsilon. So no matter what epsilon that I choose, as long as it's bigger than 0, right, it's a real number, I can find a natural number, and we call that natural number n, so it's a positive counting number. I can find a natural number, little n, such that 1 over n is less than epsilon, so it's to the left of epsilon on the number line. And the first thing we notice, by the way, is that because little n starts out as a natural number, that means in particular little n is positive as a real number, and therefore its reciprocal will also be positive as a real number, but that's a statement that we should probably think critically about if we get the opportunity to do so in a minute. But if we can agree that 1 over n is positive, then the claim we're trying to prove is that 1 over n is in between 0 and epsilon. So in our picture, 1 over n is here. And the spirit of the argument here, as most of you have put your finger on already, is that because the Archimedes principle tells us that these natural numbers don't have an upper bound, they go on forever and get larger and larger and larger, our goal is to show that their reciprocals do the opposite. They get smaller and smaller, and what we would say in analysis is that they accumulate on 0. No matter how close we get to 0, we can get closer with one of these elements. That is actually what we're trying to prove here, because our assertion is supposed to work no matter how close to 0 we pick this little epsilon. And that's what this group's proof has done so far, right? They've said that according to the Archimedean principle, because the naturals have no upper bound, the 1 over n's approach close to 0. And what I would say is, approach is a word that we don't get to use just yet in our course, because that sounds like a claim about a limit, and limits are big business in real analysis, business that we're not quite ready to undertake just yet. So we may have to choose a different approach for this proof, and one that hews as closely as possible to what we do know at this point about the real numbers, which is not a whole lot. More or less, it's limited to what's on this list, right? The axioms that define the field properties of the real numbers, which are, by the way, the axioms that build up the arithmetic of the rationals, as well as the axioms about order that tell us how greater than and less than comparisons work in our number system, and then also our axiom of completeness, right, that tells us that every non-empty bounded above set has a supremum, and that supremum is a real number. So that's really pretty much all we know in addition to the Archimedean principle. So we don't get to use any fancy calculus words like approaches or limits on or accumulates on or anything that we have to earn later in this course. So let's talk proof structure for a moment. The statement that we're trying to prove is first and foremost hypothesized, predicated on a universal claim. It's saying for all epsilon greater than 0. So our proof has to be a proof that works no matter what positive real number epsilon is chosen. So that choice is not given to us as proof writers. And that means that we should make peace with that immediately in the proof and start by saying, let's let epsilon be chosen for us by the hand of fate. We get no control over this. And we'll say greater than 0 to reinforce that it's being chosen according to the hypothesis of what we assume in our proof. Be chosen. And it's not chosen by us, the proof writers, it's chosen by the blind hand of mathematical fate. What we're then to do is we're then to discover a value of n, which is a natural number, which meets this criterion. So wherever we're going in this proof, we need to be able to show the reader where this n comes from. We may provide a formula for it, we may demonstrate that it must exist in some other way, but we have to, that's our burden of proof, is we need to show that this little n exists. So, at some point, we'll probably end up making a statement like, let us define. So this is the proof writer making a choice. And then we're going to have to say how it is that we're defining this little n. And then whatever n that we define here needs to satisfy this last condition in the proof. And so we know how our proof is going to end. Therefore, 1 over n is less than epsilon, completing the proof. So our proof has a beginning, an incomplete middle, and an end to it. And it's now kind of our job to figure out how to make this definition. If we can figure out how to make that definition appropriately, then the rest of our proof is structured in for us already. The key is how to connect this epsilon, which is the only thing that we know at this point in the proof exists, right? Connect this epsilon with our n somehow. The way that we define our n probably depends on the value of this epsilon. You can think, the smaller that I choose epsilon, the closer to 0, then probably the larger the value I'm going to need for n, such that its unit fraction is between epsilon and 0. So there needs to be some relationship between how we define n, or how we characterize why it exists, and the value of this epsilon, which was chosen for us by the hand of fate. So here's my hint. My hint is that ultimately we need to introduce a reciprocal into this mix. But at this point, it's really hard for us to say whether epsilon is greater than something, but maybe we can take this inequality and rewrite it in such a way that changes this sign from a greater than to a less than. Or maybe a better way to say it is to change this assertion, this thing we're trying to prove, from a statement about 1 over n into a statement about n itself. So try turning this inequality from a statement about 1 over n into a statement about n. And the key here is if we take the reciprocal of both sides, so I'm kind of doing that thing I'm not supposed to do, and I'm working from both sides of a proof, but if you'll forgive me, taking the reciprocal of both sides is going to turn the left-hand side of this into an n. It's going to turn the right-hand side of this into a 1 over epsilon. And it's going to turn, and this is the key, it's going to turn this inequality symbol from a less than into a greater than. And so these two inequalities, if we can substantiate why they are equivalent to one another, the one we're trying to arrive at is something we don't know how to deal with, but the one up here seems like something that Archimedes should be able to tell us something about. Okay. So how can Archimedes, and this is where I'll end this hint, how can Archimedes help us to complete this sentence? Let us define n to be a number which is greater than 1 over epsilon. But the question is, what kind of number? If you can figure out how to plug in Archimedes into this sentence, and then also how to justify this reversal of the sense of the inequality, then you have the proof in this. But it's filling in those two blanks that's the interesting bit.